Hello coders! In this video, we will see the next question from our LeetCode 75 list, which is binary search tree question. And let's see what the question. The question is search in a binary search tree. The binary search tree basically a tree in which we have a node which will have maximum 2 child nodes, and in that child node the right node will be the greater than the node. It means the value of that node. Value of the right node will be the greater and value of the left node will be the smaller from that node. Okay, you can understand it like a node. You can consider it as a parent node. Now it will have two child nodes. One child node will be at right and one child node will be at left. The value of right child will be greater than the value which is the parent node, which the parent node have, and the value which is at which will left node will have, that will be less than the value of the parent node. Okay, that basically means the binary search tree. If we see a first example here, root node is 4, 7 is greater than 4, so it is at right. Then we can see at left 2 was the less, so we went to the left 2. Then we have a 3. 3 is less than 4 but greater than 2, so it is less than 4. That's why it is at left of 4, and it is a greater than 2. That's why it is at right of 2. Okay, then we have 1. 1 is less than 4. Yes, it is less than 4. Then 1 is less than 2. Yes, less than 2. Then it is at the left side of the 2. Okay, so yeah, this is a binary search tree, and what the question is, find the node in the BST that the node's value equals well, and return the subtree rooted with that node. If such a node does not exist, return null. Basically, it is saying you need to find a node with value well and need to return that node itself. And if you return that node, the basically don't just return node, return that whole subtree associated with that node. If you return that node only, that will also work, cause that node will contain the address of the next address of its childs, and childs will contain the address of its next node, and likewise we will have a subtree. So yeah, let's see how we can solve it. First, I will say ki let's come to the your code ID, and yeah, I'll say ki if my root equal to null, if my root is null, then can I find anything? No, right? So I'll return null. And yeah, now I will see ki my root's value, or I can say here itself, if my root equal to null, then I can return root itself. And one more thing, if my root value equals to value, then also I can return root, right? So I'll write these two conditions, ki if my root is null or my root value is well, then return that root. Then I'll check if my root's value, if I don't find ki if my root isn't null and if my root values isn't not equal to value, then what I will do ki I'll check if my root value is greater than value. If it is, then what I will do ki if my root value is greater than value, then that valued node must be at left, right? So I'll return the same thing. Go to the left and search that value. Root. Go to the left. So go to the root's left and search for that value. And what if ki it is not like that? Ki if my root's value is less than value, if my root's value is less than value, I'll return. If my root's value less than value, then that valued node will be at right, cause I already told in binary search tree the right node value will be greater than the actual parent node, and the left node's value will be less than. So if my root value is less than the actual node value, then that node value will be present at the right. So search that node at right. So I will say ki return this. I return to the right and return this. Okay, done. I'll run it. Oh, it is saying ki something should be written. So what I will do ki I'll say this, cause here we have checked if root value equal to val. If it is equal to val, I am returning root. If my root value is greater than val, then going to the left and returning that value. If it is not equal and if it is not greater, then it is less. So I don't need to check if it is less or not, and I'll return this. I'll submit it. Yeah, it is accepted. So yeah, what the time complexity for this? The time complexity for this question is big of height, cause as we are doing recursion here, and for the recursion it number of internally it uses stack and number of function calls will be the height of the tree. So I'll say the height. And space complexity for this, sorry, space complexity will be big of h, cause as I said ki it internally it is using stack, and on that stack only function call will be there. Number of number of function call is equals to height of the tree. So space complexity will be big of h and time complexity will be big of n, as maximum we can visit all nodes. And yeah, that's why time complexity will be big of n. That's it for this video, and we'll meet in next video. Till then, bye.